Napier's giant snowball, the ridiculous errors that John Napier had to contend with in computing logarithms. It is the early 17th century, and John Napier is working on a massive computational project that will define his legacy. He is trying to compute the first table of logarithms, a brilliant idea that he has invented to transform the process of multiplication and division into simple addition and subtraction. However, Napier makes a terrible discovery while checking the accuracy of his calculations. The calculations have massive errors, not just some calculations, but all of them. These errors are not located in the primary digits of his calculations, but only in the last half of these calculations. He has checked and double-checked his math, and there are no mathematical miscalculations that can account for these errors. He concludes that the errors are simply the result of rounding numbers, a process made necessary by the fact that he can only compute so many digits. Usually, rounding errors are too small to worry about, but this calculation is different. Rounding errors grow exponentially in his calculations and wind up to be 1,000,000 times larger than when he began, just due to the process of doing computations on computations. He is encountering snowball error, but in his case, the snowball is really more of an avalanche. Napier decides the only way to deal with this issue is to compute more digits. He computes 14 digits so that he can throw away 6 and still have 8 good digits that he can publish. He sees no other way forward. Why did Napier's calculations have such ridiculously large rounding errors? Why did Napier's calculations have such enormous round-off errors? It turns out the calculations that Napier was trying to do was enormously unstable. Let's do an example to find out why. So, in this exercise, we're going to start with x equal to 1, and then 0.5, 0.4, 0.2, 0.1, and then we'll continue dividing by 10 till we get to 1 over 10 million, and then we'll add 1 to 1 over 10 million, we'll get a, and we'll square it, and we'll square that number again, and then a5 will be a4 times a1, a10 is a5 times a5. We'll continue until we get a to the 10 million. That will be the number eta. It'll be clear when we do the example how to do it. And then we'll use the following approximation, which point out that there's no way that John Napier would have known about this. We'll just use it to check our work. So let's go to the spreadsheet and see how to do these calculations and calculate the percent error. So starting off here, we start with 1, 0.5, 0.4, and then 0.2, 0.1, and the next one will be 1/10 of 0.5, and 1/10 of 0.4, 1/10 of 0.2, and 1/10 of 0.1, and we'll just continue until we get 1 over 10 million. Okay. And now we'll add 1 to that number. We'll call that A. And then we'll square that number. And then we'll square it again to get a to the 4th. And then a to the 5th will be a to the 4th times a to the 1st. And then we'll square a to the 5th to get a to the 10th. And we'll continue to get a to the 100th, a to the 1,000. We'll just bring it all the way up to get a to the 10 million. That number looks a lot like E. Bit of a coincidence though, but it's not E, it's eta. And we're going to use this approximation to figure out exactly what eta should be in the calculation, exactly to 16 digits. We'll exponentiate that number to get eta. We'll compare it with E. It's actually different than E. Okay. So, to calculate the correct value of A, we'll use the natural log of eta, and we'll multiply it by that log of A column. And we'll calculate the percentage error the standard way. And that is a big error. 4.5 times 10 to the minus 10, that's 4.5 million machine epsilon. That is a huge error. And notice something about the errors. The errors kind of repeat, except that the digits repeat, except that each one, 4 previously was 1/10 as big. So the errors are growing really rapidly. They're growing exponentially. So why did Napier's calculations have such enormous errors? The calculations are very susceptible to round-off error. If the round-off error is of x is epsilon, then the error of x to the k is k times epsilon. Oh dear, this is a snowball that's growing and growing and growing. Yeah. So let's talk about some red herrings. The first red herring. This example actually differs from Napier's calculations, therefore it doesn't show anything. Well, it's true, these calculations are a bit different, but the essential factor about the errors, they are identical. They are really the same errors that he faced. And the next false claim is that because eta measures E with error, this is related to the round-off error. No, there's no connection between those two. Eta is its own calculation. You can calculate logarithms with any base, base 10, base 2. You could use base eta. That would be fine. You just have to calculate eta correctly. You have to be able to calculate it the right way. And we'll be able to do that in example 2. Okay, orange herring. This is a not completely true claim, but not completely false either. It's unfair to blame John Napier, a mathematician who lived a long time ago, for math he didn't know about. Yeah, that would be unfair. I'm not claiming that he should have known about calculus, other advanced math. Some of the problems he was facing were simple arithmetic, but even simple concepts that aren't hard to understand might be hard to think of if you've never encountered them before, which would have been true in Napier's case, so I think it is worth keeping this in mind. So the first concept that would have helped Napier's calculations was the equivalent of floating point arithmetic. And in his time, he was working with fractions, not decimal points, but that would have made it easier to understand floating point arithmetic, and I think he basically did. If you're calculating something to n digits, you need to make sure that the numerator was at least n digits large. Otherwise, you're losing digits. That's kind of common sense. A simple example will illustrate the point. Suppose you're calculating a sequence. You start with 4 over 10,000. And you do this simple calculation, 2x plus x squared, several times. And we're going to keep 8 digits. So yeah, we're starting with 4 over 10,000. And we're going to compare the fixed point and the floating point methods. And in the first few calculations, we're not going to see any difference because there are no errors. But in the third row, we will see errors. In the fixed point, we've rounded to 6 digits because the numerator is 6 digits large. That's how big the denominator will accommodate. In the floating point, we allow the denominator to be larger. That allows a bigger numerator, 8 digits. But then you've got the issue that between 2 and third row, we had to divide numerator and denominator by 10 to keep the numerator an 8-digit number. That's kind of confusing. Not too confusing. I think he could have handled this. I don't think it would have been an issue. Another way of doing it would have been to allow the numerator to be bigger than 8 digits, but just pad in the extra digits with zeros. That would have worked as well. So let's look at some numbers that we calculated in exercise 1. Okay, these numbers look like 1 plus r, where r is a very small number. And I would like to be able to see what r is separately, because I can see that we're losing the digits that I want to know about. The digits in the second column, the 4, 5, where are the digits beyond the 4, 5? I want to see those. If I could calculate them separately, I could perhaps get more digits. So the idea of splitting the calculation into the form 1 plus r is called the interest-only calculation. Here's an example that illustrates the idea. Suppose you have an investment that earns 2% first year, 3% in year 2. What is the total return over a 2-year time period? It's close to 5%, but that's not the right answer. It's 1.02 times 1.03 minus 1, which is 0.0506. But there's another way we could have calculated that. We didn't have to add and subtract 1. We could have just added 2%, 3%, and then the product of 2 and 3%. In general, it's R1 plus R2 plus the product of R1 times R2. That's the interest-only calculation. And the idea behind this is we can see more digits now. The analogy is it's hard to see stars during the day because the sun is too bright, but at night, with the sun removed, distant stars are now visible. The 1 is like the sun because it starts the count of significant digits. Without the 1, the start of the count is with R1 plus R2, which is a much, much smaller number. So in exercise 2, we're just going to repeat exercise 1. But this time we're going to do it a little bit better. We're going to do it with the principal and interest, calculating the interest with the interest-only calculation. We're going to use the same approximation for eta. That approximation's fine. It will allow us to calculate the digits that we're missing. Let's go back to the spreadsheet. Okay, so we're going to put these calculations side by side, and we're not actually changing the log of A column at all. But we're splitting the A into a principal and an interest. The principal is always 1. The interest will be R. 1 plus R is going to be A. R starts off as X, but then the next calculation is 2R plus R squared. And again, this is 2R plus R squared. And this one, next one is going to be R4 plus R1 plus the product of R4 and R1. And then the next one is going to be 2R5 plus R5 squared. And we're going to bring those calculations up. Okay, we're going to add 1, add the principal and the interest, and that number is close to eta. That should be eta. We're going to compare it with the formula that we had been given before, which is in cell D3 there. In general, it's D3 times the log value, which is in column J. We're going to calculate the percentage error, and I would be happy if this number were about 10 times machine epsilon, because there are a lot of calculations here. Oh, it's 2 times machine epsilon. That's excellent. That is absolutely excellent. In fact, all the calculations are excellent. Only a few of them have any measurable errors at all. And massive improvement, 2 million times better. Let's look at some of the digits and some of the actual calculations. So we compare the standard and the interest only. And on the second row, the number ends in 45. Look at the column next to it. It ends in 45. 0, 0, 0, 0, 1, 2. Those are all digits we didn't see before. Okay, the next row. 495, it ends. Over the next column, 495, 0, 0, 1, 6, 1, 7. Those are all digits we did not see before. We're seeing more digits now. That's why we're getting a better value for the calculations. So exercise 3. Let's do the calculation again, but let's go all the way down to 10 to the minus 16. Why? Because we want to see if we can calculate e this way and calculate natural logs this way. Could you? Well, let's find out. There could be a lot of round off error this way, because there are a lot of calculations. We don't know if it'll work or not. Let's just see. So this calculation is actually very similar to exercise 2. We're just going down to smaller numbers. The interest, the R starts off as x, and then the next value is 2r plus r squared. And then this one is going to be r4 plus r1 plus r4 times r1. Okay. We bring those four calculations up all the way to the top. And that does look like, if we add 1 to the interest, that looks like E. How close is it? I would be happy with 10 machine epsilon, because there are a lot of calculations here for an error. Oh, it's about 2 times machine epsilon. That's excellent. Very, very happy with these calculations. It turns out this is an excellent way to calculate natural logs and the corresponding exponential function. Okay, time to close the spreadsheet. Thank you.